Okay, welcome to the set theory seminar. So today our speaker is Neil Barton from the University of Constance in Germany, and he is going to speak on countabilism and maximality, or some systems of set theory on which every set is countable. By the way, in the chat you can also find a PDF of this handout so that you can follow along. So anyway, go ahead, Neil.
Good. So thanks very much. Thanks very much for the invite. As Gunther said, the PDF of this handout is in the chat, so you can follow along and pinpoint any questions you might have. This talk, actually, I gave a version of this talk several years ago in New York, and the kind of closing moral there was that we needed some more results, and I think thankfully we've actually found some really interesting results here. So just a comment on the title before I get going. So I've kind of given it two titles, one countabilism and maximality, and the other one some systems of set theory on which every set is countable. And the reason for that is that there's a kind of very philosophical aspect to this talk that we'll see. Can you come up with nice theories for people who think that every set is countable? And there's also a kind of more mathematical interest in it, that the systems that we come up with have some sort of quite nice mathematical properties. So we'll see that as well. So there's a sort of division between something more philosophical and something more mathematical here. And because this is a set theory seminar, I'm going to focus primarily on the mathematical part. I've also chosen to do a kind of handout approach here. And I'm interested to see how that goes. If people have any feedback on that, how well it's worked with Zoom, then I'd be interested to know. And just a note before I get going, this is all joint work with Cy Friedman. So credit to him too. Okay, good. So please ask questions throughout. Let's get some motivation going. So let's just start by noting that ZFC-based set theory is a very nice mathematical theory, and it's very nice from a philosophical perspective as well. So consider the following desiderata on a foundation, and this is taken from some of Penn-Maddy's work. We have generis arena. This is the idea that you can find representatives for your usual mathematical structures, natural numbers, the reals, and so on. Closely linked is the idea of having a shared standard of proof. So potentially, if two mathematicians disagreed, if you had the time and patience, you could characterize their proofs in ZFC-based set theory and compare them. And it could give you a standard for correctness, or at least an idealized standard of correctness. Closely linked to this is the idea of metamathematical corral. So this is the fact that we are able to provide a theory in which we can investigate different principles, relative provability, consistency strengths, and the wide variety of models of different axioms. And then, given this hierarchy of consistency strengths that we're all familiar with, we get a kind of risk assessment out of that. So we have a certain degree of confidence in various theories, perhaps based on an underlying conception. And we think that things like ZFC give us a degree of confidence that other theories are consistent based on relative large cardinal strength. Okay, so to these we might add, and thinking about the ZFC context, the following motivational challenge. So motivator theory with a substantial degree of large cardinal strength on the basis of an account of the global nature of the universe. So with this, I want to exclude the idea of just asserting particular axioms in a piecemeal fashion. So for instance, I don't want to just assert there is an inaccessible cardinal, let's say. I want to assert something about the nature of the universe. And the example I'll consider is reflection principles, at least for the ZFC theorist. So let's just note that for all these kind of philosophical motivations up here, ZFC perhaps combined with the iterative conception and perhaps with reflection principles added. So those are principles that state that if phi holds of the universe, it holds of some V alpha. These give a really, really nice response to all these kind of foundational needs, right? So, generous arena, you can find all your reals and natural numbers in the universe of sets as standardly presented. That gives you, naturally shared standard and meta-mathematical corral. I mean, in particular, ZFC set theory just is the place where this study is conducted in some sense. And then for risk assessment, we've got this very nice picture of the iterative hierarchy. And if you think that something like maximality, so the idea that the universe should be as large as possible, you have a kind of motivation for why you should accept, let's say, large cardinals, right? Second order reflection, for instance, will give you inaccessibles, Marlowes, a huge amount of stuff below the level of 0 sharp. So ZFC is very, very, very nice, right, regarding these kind of philosophical constraints. But there's a puzzle that comes out of forcing here, and this is a kind of sort of very obvious puzzle in some sense, but it's still something that I think has motivated a lot of the kind of research around ZFC-based set theory. We've seen it in the work of a lot of people in New York, in fact, regarding these kind of multiversist ideas. So here's the puzzle. I call it Cohen's paradox here. I think I'm actually leaning more towards the Cohen-Scott paradox, and it depends on these three observations. So first, Cantor's theorem, right? We think there are uncountable sets. Second, if you give me a model of set theory, right, I can pick any cardinal in that model, cardinal kappa, and I can add a function that collapses it to omega in the extension. And observation C, not only can I do that, if I want, I can make P, the power set of omega, larger than the particular cardinal kappa I started with. Okay, so then there's this kind of informal paradox we might get going. So we think there are uncountable sets, in particular the set of all real numbers, for instance, by Cantor's theorem. But by observation B, we could, in some sense, collapse any set to the countable by adding a surjection from omega onto X. And in particular, by observation C, we could make the reals bigger than a particular set X. So then this puzzle is, look, on the one hand, you think that V should contain uncountable sets, but on the other hand, if the universe does contain uncountable sets, it appears to be missing all sorts of collapsing generics for partial orders, and the reals seem smaller than they might have been in some sense. Okay, well, there's a standard response here, right? And that's that, look, the relevant models you talk about when you say that the reals might have been bigger are unintended in some sense. So perhaps I'm working really in some countable transitive model and the reals that aren't in there are still living in V, or perhaps I'm talking about some strange Boolean valued structure over V, but it's not the case that, the reals really might have been bigger. This is the kind of standard response. But even if you have this kind of universe view, this is only one of the available responses, right? A different approach would be to say, look, it's the interpretation of Cantor's theorem that's at fault, not the kind of possibility regarding the existence of sets. So one motivated thing you might do here is say, well, look, I'm actually moved more by the possible existence of these sets. I'm going to deny the power set axiom. I'm going to hold that every set is countable. And I'm going to think the continuum is a proper class. Okay. Now, this seems like heresy, right? But I'll just appeal to the wisdom of Dana Scott, and this is why I've called it the Cohen-Scott paradox. He says this very nice quote in the foreword to Bell's book on Boolean valued models. So, and he says, I see that there are any number of contradictory set theories extending ZFC, but the models are all just models of first order axioms, and this is weak. I still think it should be possible to have strong axioms which would generate these types of models as submodels of the universe, but where the universe can be thought of something absolute. Perhaps we'd be pushed in the end to say that all sets are countable and that the continuum is not even a set when at last all cardinals are absolutely destroyed. Okay, so it's at least an idea that has been appealing to certain people, but I think there's a challenge here, right? We've seen that ZFC is very nice foundationally. Can we put the counterabilist, the believer that every set is countable, in a similar position to the ZFC uncountablist with respect to the foundational constraints, and including the motivational constraint and motivating principles on the basis of maximality? Okay.
There's also another, can I just interject something?
Yeah, please do.
So, I mean, one of the desiderata that you listed in the beginning was this wide arena, or what you called it, like that there should be. But I mean, if the reals wouldn't be available as a set in such a model, right? So you would lose. You're trying to make it really large, right? But in a way, you're not achieving that in this sense. That you're missing the set of reals now.
It definitely seems weird to prioritize all these generic filters over like power sets, but carry on.
Good. So we will exactly deal with this in section 7. This is going to be where section 7 is going to be where we talk about exactly what mathematics looks like here. And look, there has to be some trickery involved somewhere, right, to get these the things we want to say, for instance, about the reals to work. And there is going to be some trickery, and at a certain point, how much trickery there is going to, depend somewhat on intuitions. But in any case, all I'm going to argue here is that, look, there's at least a kind of motivated perspective on which we get close, and we get some, I mean, even if you don't find anything in here convincing, there's going to be some kind of interesting mathematics about models of second order arithmetic on the way. So, for instance, sections 2 to 6 is just interesting mathematics, even if you don't buy the kind of philosophical stuff. Okay, so here's what I'm going to do. We're going to talk about ZFC minus power set. This will be familiar to a lot of people and how some care is required there. We'll then talk about some more stuff that will be probably pretty familiar. The idea of just brute forcing large cardinal strength in with determinacy axioms. And then sections 3 to 6 will examine a particular kind of approach one could take to getting some strength out of Counterbliss pictures. And the basic idea is that we take inspiration from forcing axioms here. And in particular, we start looking at very strong principles of absoluteness to outer models. So here we'll get something that's very weak. It doesn't even break V equals L. Section 4, we'll see something that breaks V equals L, but still gets us no large cardinal strength. Section 5, we'll see an axiom that goes too far and is inconsistent. And then section 6, we're going to find something that's consistent relative to ZFC plus projective determinacy, but also implies that zero sharp exists. Then I'll talk a little bit about what mathematics looks like and present some open questions at the end. Good. So before we get going, one issue that needs to be dealt with in the setup is that what do we consider the Counterbliss base theory to be, or at least if we're open to the existence, if we're open to the failure of power set, what theory do you want to take? And the natural answer is, well, you just write down the axioms of ZFC and delete the power set axiom. Okay, but we know this is problematic. In particular by work of Vika and collaborators. We know that the various and Zarach, you know that various equivalences one normally has in the presence of power sets disappear. And in particular, just keeping replacement does not preserve collection, and versions of the axiom of choice become non-equivalent. So we need a little bit of patience and care in setting up the theory we'll use. Okay, and we can distinguish the following theories. So ZFC minus is ZFC with the power set axiom removed, and AC formulated as the claim that every set can be well ordered. And right from the off, I'll just say that this is a sufficiently pathological theory that really this is not going to appear at all in this talk, but it's one of the theories out there, so we should mention it. Okay, so ZFC minus, or what I'll call ZFC minus, is the replacement axiom substituted with the collection and separation schema. Okay, and then we're going to have ZFC ref is the following, is ZFC minus with the following schematic reflection principle added. Okay, and this just says that for any particular phi, you might consider if phi holds, then it also holds in some transitive set.
Neil, can I ask a quick question?
Yeah, please go ahead.
Do the phi here, do these allow parameters?
Yes.
Okay, great. Thank you.
It's essentially, I mean, it's essentially the Levy-Montague reflection for when you don't have V alphas is just the idea one wants to have here. And I'll refer to this as the first order reflection principle, or I might just talk about reflection, or as we'll see, I might talk about just dependent choice in particular context. Okay, but that'll come in a second. In any case, by MBG minus and MBG minus ref, I just mean the corresponding versions of MBG where you delete the relevant second order axiom and substitute in the correct second order predicative axioms in their place. Okay, good. So we know that these are distinct, and we also know that there are models of ZFC minus plus count. This is what I'll use to mean every set is countable, in which reflection fails. And interestingly, first order reflection is equivalent modulo ZFC minus to the following dependent choice scheme. So this is the scheme of assertions for each formula phi x, y, z and parameter a. If for every x there is a y such that phi x, y, a holds, then there is a particular omega sequence such that for all n, xn plus 1a holds. So, in plain English, if a definable relation has no terminal nodes, you can make omega many dependent choices on its basis. So this is a kind of schematic dependent choice principle. Now, I mean, this is sort of quite a weak kind of choice in some sense, so albeit class choice. So I think it's very plausible that you should want your principles to be consistent with this principle added, and in particular then either ZFC minus ref or MBG minus ref, and this will pop up later, and this is in some sense the theory that we want to have in the background as the strongest possible theory. Okay, good. So what's the first way of getting strength on this picture? Well, first point, there are statements of set theory concerning second order arithmetic that yield substantial large cardinal strength. And this will be known to lots of you, but it bears mentioning, and also this will allow us to set up the version of zero sharp exists that we're going to be using here. So for instance, if we're looking at, say, zero sharp exists, we do need to be careful again exactly how we're going to set this up, right? So for instance, you could say every uncountable cardinal is indiscernible in L, right? This is clearly useless in this context because we might not have any uncountable cardinals. So what we're going to use is the following. So this is in ZFC minus or MBG minus. Zero sharp exists will be taken to mean that there's a definable club of L indiscernibles. This you might think is higher order, right? What the heck is this definable doing? But by work of Silver, you can show that if there's a definable club of L indiscernibles, then there's a unique delta 2 definable such club. And delta 2 definability just is definable. So this can be all made nice and formalizable. Okay, so just some quick facts that will be probably quite familiar. So over NBG minus, we could also have ZFC, C minus here. There's no requirement that it's in NBG minus. Zero sharp exists implies that there's an inner model, i.e. a transitive model containing all the ordinals. For ZFC plus, there's a proper class of inaccessible cardinals, okay? How do we do this? Well, I mean, this is sort of familiar stuff. This is an R result. Every silver indiscernible is inaccessible in L. And so the existence of zero sharp implies the existence of a proper class of inaccessible cardinals. And these indiscernibles are all elementary in L. So we know that L models ZFC. So we get lots of large cardinals in a particular inner model, namely L, out of this principle of second order arithmetic, even when every set is countable. Okay. And this is going to be part of the trickery we pull later, is just to say, look, you have this, very fat model that satisfies, let's say ZFC minus ref plus count. But look, if you want to, you can always go to some impoverished inner model in which ZFC holds with large cardinals added. Right. Okay, and now it's easy to go further. So by, well, very non-trivial results, but you can, it's still not problematic in the ZFC minus context. So with projective determinacy, one gets inner models with wooden cardinals, in particular n many for every n in n. And regular Krapp's dissertation has a really nice result that from boldface pi11 determinacy and the boldface pi12 perfect set property, one can obtain inner models of ZFC plus every set of ordinals has a sharp. So this is, very nice. We get all these large cardinals out of these principles of second order arithmetic, and we don't need uncountable sets floating around to do this. Okay, and as I said, in this context, your ZFC models are there. They're just impoverished. They're missing all sorts of collapsing functions. Okay, but these principles do not seem to be, okay, this kind of sets up the general idea we'll be going for, gives us a chance to say what zero sharp is going to be that we'll be using later, but they aren't really well-motivated principles in some sense. I mean, they're interesting principles, but they don't clearly correspond to the way the universe might be in any sort of broader, more philosophical sense. Donald Martin has this nice quotation, so is PD true? It is certainly not self-evident. So maybe we want a more general idea to try and get out at least things at the level of zero sharp. Okay, good. Any questions before I continue? Okay, so far so well known. Okay, let's see if we can do better, and this will be a kind of warm-up section for what comes a bit later. So our suggestion is to view the maximality of the universe, if you're a counterblist, via different kinds of saturation under possible sets. So we want to say, look, there's lots and lots of subsets floating around. Okay, so the first strategy we're going to take, and this is in the end going to be quite weak, it's going to be in fact equivalent to every set is countable, is going to be a kind of forcing axiom strategy where we just assert the existence of lots of generics. Okay, so when you're in the ZFC context, you have to be a little bit careful about the forcing axioms you formulate, right? For instance, if you assert that Martin's axiom holds for a continuum-sized family of dense sets, you'll get a contradiction. But given that we haven't committed to the existence of uncountable cardinals in this context, we can formulate the following axiom, which we're going to call the forcing saturation axiom. And that just says if P is a forcing poset and D is a set size family of dense sets, then there is a filter G intersecting every member of D. So just forcing axioms, but we do it in ZFC minus, and we take away the any requirement on the kind of forcing we use or the size of the family of dense sets we use. Okay, now we have the slightly unfortunate fact that forcing saturated set theory is just equivalent to every set is countable. Okay, so how does one do this? Well, to get to every set is countable, you just do what you would expect to do. You take col omega alpha for any particular ordinal alpha. You can get that via the definable power set that holds in ZFC minus. And you then get a collapse from alpha onto omega. You need to define the right dense sets and things, but it's not too problematic to do. Going in the other direction, you're just going to enumerate the particular family of dense sets you have. So you enumerate your family in order type omega. And then you know that your partial order can also be enumerated in order type omega. And so you just define a function that goes up through the dense sets, picking the F least P in the next dense set. And then you just look at the range of this function and you'll get something that generates the relevant generic. So just using enumerations to hit particular dense sets as one would expect. Okay, so once we have this in play, you have the very immediate fact that, well, firstly, this forcing saturated set theory, this gets you no extra strength, in particular because it's true in the H omega 1 of any particular model you like, or if omega 1 is odd, it's just true in that model. And in particular, H omega 1 relative to L is also going to satisfy forcing saturated set theory, so it doesn't even break V equals L. So very, very weak. Okay, so once we get countabilism out of some sort of saturation idea, we don't get breaking V equals L and we get a very weak theory. So I don't think this is necessarily a death blow to the theory. In fact, a similar thing happens in the ZFC context, right? So, ZFC is consistent with V equals L and it's not especially strong once you've learned about large cardinals. But it can be strengthened using large cardinals to break V equals L, and that's what we'll see later in the Counterbliss context. Okay, good. So that's the warm up. That's the warm up done. The kind of forcing axiom route doesn't work, so we need to go for something a little bit stronger in some sense. And the core idea will be to use absoluteness. So recall at the start, I talked about reflection on the ZFC picture. So this is on the ZFC picture. And there it's a kind of rank reflection. So from properties of the universe to properties of initial segments. And what we're going to be doing here is looking at absoluteness between the universe and possible extensions of the universe. So the idea is that, any way you can dream up new sets outside is already realized within your universe. So it's a kind of width absoluteness rather than height absoluteness that's motivating the principles here. Okay, good. So I just talked about rank absoluteness. So this principle is going to break V equals L, but unfortunately, it's still going to be very weak. But let's note that ideas of absoluteness already exist in the literature on bounded forcing axioms. So this is a definition from Bagheria. He gives us a version of the bounded proper forcing axiom. You say that V satisfies, a model satisfying ZFCs satisfies the bounded proper forcing axiom in this absoluteness sense. If whenever phi is a sigma 1 formula with parameters from P omega 1, if phi holds in a forcing extension obtained by proper forcing, then phi holds in V. Okay, and this gives you an equivalent characterization of BPFA with some substantial large cardinal strength. So this is we're going to motivate a similar idea. So Bagheria says, in the case of MA and some weaker forms of PFA and MM, some justification for their being taken as true axioms is based on the fact they're equivalent to principles of generic absoluteness. They assert, under certain restrictions that are necessary to avoid inconsistency, that everything that might exist does exist. So this is our kind of idea. But because we're in the ZFC minus context, we don't need to worry so much about these particular restrictions. Okay, so taking this to the ZFC minus context,
Neil?
Go ahead. Yeah.
I was just, I just was wondering, I mean, I'm trying to kind of get the, understand the goal here somehow. And it seems to me like, is it right to think of the goal being you want this model, you want a model of your theory that thinks everything is countable to look like, so to speak, the ultimate thing that you would approach if you start in a model of ZFC and you do all the kind of forcing you want to do. So for example, would you want to have that if you're in this, would it be a reasonable axiom, so to speak, in your, or desired axiom in your theory that for every set, L of X is a model of ZFC?
So the proposal is that for any set X, L of X models ZFC.
Yes, that would be something I would think should hold in a model like what you're trying to build. That it's like this model that you're in, it has it thinks everything is countable, but if you form, if you form L in there, it should be a model of ZFC, right?
Yeah. So this will follow, for instance, from this axiom, right? For every X sharp exists. Yeah,
for example, yes.
Yeah, it's a good. This is an interesting idea. In the end, we're going to get 0 sharp, but I don't know if we get any more out. But this seems like a reasonable thing to say, right? We want to transcend L of X in some sense for any set X. I just don't know if it holds in the picture we're gonna end up with. But this is a really nice question.
Or it would be like, for example, a scheme saying like, whenever you have a formula that defines an inner model of ZF, and you have a forcing in there, there's a generic in V for that inner model. Like stuff like that should hold, right? I mean, I'm just trying to understand whether that would be the kind of thing you would like to have as a consequence of your
Yeah, I
axioms, right?
think so.
Yeah.
And in fact, one of the things we're going to consider at the end is when you want to have a kind of, if you still want some sort of iterative picture, the natural class of models to consider is of that kind, where you start with some particular like inner models of ZFC and you consider the Col omega order extension of these models.
Right. Oh. Okay, I just saw that Andreas Blas has raised his hands.
I want to a quick comment about your comment. And from the very first page of this, Cy Friedman is involved in this research also, and he may have something to say about this in the direction of what if X codes the universe, for example.
Right.
Right.
Yeah.
So it's not at all clear that if, okay, so that's a class forcing which may be beyond what we normally want to think about, but it may not be as intuitive a principle as I thought when you first mentioned it, that L of X should always satisfy ZFC.
That's a very good point. Yeah, especially since it's Psi, and he really, I think he finds the separation between set forcing and class forcing kind of unnatural in a way. So yeah,
we are
good point. Yeah,
we are going to make heavy use of class forcing later. So yeah, this is a good point. Actually, I think we'll have. Anyway, let's consider that in context later. Otherwise, I won't get through the stuff. But no, it's a great question, and Andreas's suggestion is also super interesting in this context, because a lot of the proofs we're going to do later involve passing to class forcing extensions and pulling stuff back. Anyway, that will come later. Okay, so we're going to say that we're going to have this definition of the weak axiom of set generic absoluteness. So we restrict to sigma 1 formulas because normally we want to deal with absolute properties. And we're just going to say that whenever phi A is some sigma 1 formula in the parameters A, if we have a forcing partial order and we have phi A holds in VG, which models ZFC minus, then phi A holds in V. Okay, and unfortunately, this also turns out to be equivalent to the axiom that every set is countable. The move from the WASGA to count is pretty much immediate. You just do the usual collapse. Count to WASGA is just from Levy absoluteness, which tells us that if a sigma 1 formula with real parameters holds in an outer model of ZFC, then it holds in V. And in particular, in this context, every set is coded by a real. So you get this out of just Levy absoluteness. Okay, so let's go wild and allow any sentence then. Okay, so we're going to say the axiom of set generic absoluteness holds, and then we have exactly the same principle, but we don't restrict to sigma 1 formulas. Okay, so obviously over the theory ZFC minus, the ASGA implies that every set is countable, but we also get that V is not equal to L, because in this context, we can force the existence of a non-constructible real, and therefore we get a non-constructible real in V. So we break V equals L. So you might in fact worry about consistency for precisely this point about kind of absoluteness worries. So normally generic absoluteness says that if there's a set in a forcing extension that satisfies an absolute property, then there's such a set in the ground model. And typically this underlying absolute property is delta naught because you want it to be absolute. And so you get a sigma 1 kind of absoluteness out of these kind of principles. But in fact, the ASGA is it's very weak in terms of consistency strength. So I'm actually going to skip over this kind of proof sketch because time is running a bit, and I want to show some of the more interesting stuff. The essential point is that you do an Aleph-1 product of co-enforcings Or in the case in which Aleph1 doesn't exist, you can just let this be ORed. It all goes through basically the same, with checking that that ZFC minus is preserved. And then just the H omega 1 in the forcing extension is going to be your model for the axiom of set generic absoluteness. So we'll skip over this proof. It goes through roughly as one would expect, but the core point is that what's happening here is that in the ZFC minus plus count context, everything is equivalent to co-enforcing. All set forcing is forcing equivalent to co-enforcing. So this means that you can absorb these kind of forcings into co-enforcing in order to get the ASGA out. So you just don't need to worry about the kind of absoluteness worries that appear in the normal ZFC context. Okay, so we have this neat little axiom. It's interesting. It breaks V equals L, but it's very, very weak. And we want to get strong axioms out. Okay, so let's look at this very extreme version of the inner model hypothesis, and this is going to be very strong. In fact, it's going to be pretty close to the very strongest large cardinal axiom that we call 0 equals 1. Good. So we're gonna blow everything up. So a natural point of attack to strengthen things in the current context is to look at the extensions allowed. So far we've only allowed set forcing, but you could consider class forcing. You could consider all sorts of extensions. Okay, so considering any extension you'd care to think about has already been considered in the ZFC context, indeed by Tsai and later Welch and Wooden. So we have this inner model hypothesis, and this just says that if I have a model V, modeling ZFC, if phi is true, if I can go to an outer model and I can realize phi true in some inner model of an outer model, then I can already find phi in an inner model of V. And in the ZFC context, we have to keep that parameter free. Otherwise, we could collapse omega 1, and then we'll get a collapse of omega 1 in a model, which is obviously bad news in the ZFC context. Okay. Yeah, go ahead.
Forget. How is this formalized?
Good. Yeah. So how is this formalized? Options for you. Option 1, you go to a strong class theory. So this would be like MK with bounding added, right? And then you have to check.
Sorry, can I ask a question about this explanation? Yeah. So you're saying this implies no worldly cardinals. How can you have this and also have MK, which gives you lots of worldly cardinals?
Exactly. So we in the paper in which we do that, this is with Karen and Tsai. Yeah, this is a problem, and what you have to do is you have to relax things so that the outer model doesn't just satisfy ZFC; it also satisfies this version of MK, and you have to bring classes into the picture. Okay, so this gets very fiddly very quickly. A different route that is perhaps more, I should have given the more palatable one, the more palatable route first. A different route that's more palatable is just restrict to tame class forcings. And then you have a definable forcing relation. You can do it all in terms of the forcing relation and do it in NBG, let's say. Does that help? So I would say just, we'll talk a little bit about formalization. In fact, this is coming up here. But yeah, one has to be careful here. There are different options and you have to tweak the principle in question sometimes. But that's a good point to make, Cam.
So what you're saying is I should just think of the outer models as being tame class forcing extension.
Yeah, I mean, when Tsai originally formulated this, I think he wanted it to be as general as possible. So in the context in which he works with it in the 2006 paper in Friedman, Welch, and Wooden later, you just do it all in terms of a countable transitive model, right? and just work within some larger universe. And then everything could be formalized as about this countable transitive model. Or you just do it in NBG and just read outer model as tame class forcing extension. Yeah. But these are good questions, and these are not easy questions. Okay, so the IMH is strong. It's consistent relative to a wooden cardinal with an inaccessible above, and it really has strong large cardinal killing properties. So you kill inaccessibles, but you in fact kill all worldly cardinals. Okay, so now we're going to formulate this very extreme version of the inner model hypothesis. So and we're going to do this in NBG minus ref, just to allow us to quantify over the inner models in question. You can also do this in ZFC minus, I think, minus ref, if you want to just do everything in terms of definable models. You can also substitute in NBG minus and NBG minus ref here. This requires a bit of meta-mathematical care and a couple of extra lemmas, so I'm just going to insist on the outer models having ZFC minus. Okay, but what does the principle say? Let's not put the cart before the horse. It says if you have any formula phi in the parameters A in V, if you can get phi A true in an inner model of an outer model, that should just be V in, then phi A is already true in an inner model satisfying ZFC minus. Okay, so formalizing these principles, you could go to like an NK minus type theory. For everything we say here, we're just going to work with definable class forcings, which are pre-tame and have a definable forcing relation. So we can do this all in NBG minus for sure. Okay, so it's kind of interesting question about the philosophical setup there and exactly how one wants to formulate it, but we're just going to take kind of easy formulation. Good. So some facts. So first, this principle implies count very clearly. You can just collapse any set in an outer model. Clearly, it implies that V is not equal to L because you just force the existence of a non-constructible real. But unfortunately, NBG minus ref plus EIMH ref is inconsistent. And what we're going to do is we're going to show that there's no transitive model of NBG minus ref plus EIMH ref. In fact, we're going to do this for a particular finite subtheory, but it doesn't matter because we have reflection in the picture. We have a transitive model for any particular for any particular theory just by reflection or the dependent choice scheme. Okay, so suppose that V is a transitive model of this theory. You can assume that V is countable. Of course, V satisfies count just by the IMH ref. Okay, now we need to appeal to a theorem of Carolyn Antos and Scythe Friedman, who show something about a particular context in NK. You use almost disjoint forcing and a kind of reshaping argument, but the end result is that you get an outer model of V satisfying ZFC minus ref, which is of the form L alpha R naught for some real R naught. Okay, and then we have to do another bit of reshaping using Cy and Carolyn's work. We can enlarge further to a model in which is of the form L alpha R, and in particular for every ordinal beta less than alpha, L beta R fails to satisfy collection. So you're only getting this, you're only getting collection satisfaction in the limit, right? Okay, now we apply the EIMH ref and we pull back such a real, which we'll denote by R prime, to our original model. Okay, now we can define a function. So we're going to let F beta be the least n such that sigma n collection fails in L beta R, right? So we're firing up these particular L betas, well, firing them down, I should say, into the relevant natural number. Okay, and now for each n, we're going to force to add a club, Cn, consisting of ordinals beta less than alpha, such that F beta is at least n. Right, so we force in this bunch of clubs, and now you can code these clubs into particular reals Sn, right, using the same reshaping arguments that Caroline and Cy gave. And then by the EIMH again, you pull these back into V, but now you can decode the corresponding clubs in V. And then by intersecting together all the various clubs, we can find some F beta. There's at least n for each n, but that will contradict our assumption, because then we get that L beta R is going to satisfy collection, right? So this turns out to be inconsistent. Okay, so it looks like this EIMH takes things too far. Again, I don't think this is a death blow to the counterbliss. The same is true for the uncountabilist. Elementary embedding from V into V, or third order reflection, or any of the forcing axioms that turn out to be inconsistent. Almost any axiom can be extended to inconsistency. And importantly, this includes, as I just mentioned, reflection, which is kind of our contrast case in the present context. Okay, so can we do a little better? So we're now in a position where we'd like to weaken the EIMH, but still go beyond the ASGA. And the kind of natural point of attack here is to restrict the parameters allowed. So in NBG minus, we're going to talk about ordinal inner model hypotheses. So you're going to let phi be a first order sentence with only ordinal parameters A. And then we just have the same definition. So if phi is true in an inner model of an outer model, satisfying the relevant theory, this is Z of C minus in this context, Z of C minus ref, sorry, in this context, then phi is already true in an inner model of V. Okay, so the OIMH style principles have all the nice counterbliss things we wanted earlier. You break V equals L and so forth. But pleasingly, MBG minus plus the OIMH ref is consistent relative to ZFC plus PD. So we have at least some reason to think that this is consistent. Okay, what's the strategy here? Well, we work in a model of ZFC plus PD, and you have to look in the Turing degrees given by PD to ensure that we can find a model with the right behavior. Okay, so I'm aware that I'm pushing up against time a little bit, so I will go through this proof and the next one, and then perhaps I will leave aside the discussion of the kind of how to interpret mathematics on this picture, and we can come back to it.
Neil, you have about a half an
hour. Oh, okay. I just don't want to like. Okay. Well, I'll go through everything then, but I don't want to, sort of test people's patience with this stuff. So I'll try and leave, a decent amount of time for discussion. Good. So we're going to use the Turing degrees to get a model of NBG minus plus the OIMH minus ref. I may drop, from now on, I'm always working with the ref versions of the theories. I may just drop this just for the sake of syllables. Good. So let's let, for any set of ordinals X, let's let MX be the least transitive model of ZFC minus ref containing X. And we know that such a model is of the form L beta X for some beta. And in particular, because it's of this form, it satisfies the DC scheme. So we get we get ZFC, we get ref for free, or reflection for free. Okay, and now we're going to define a function that's going to be useful for finding models with the same theory. The strategy here is to look at the Turing degrees, look at Turing equivalents, and use this to get models with the same theory, and we're going to use a particular function to do this. So for any particular countable ordinal alpha, let alpha be a real R alpha such that alpha is countable in MR alpha. And for all y in which R alpha is recursive, we have that my has the same theory with parameter alpha as MR alpha. Okay, so this is a perfectly well-defined thing. And the reason it's well-defined is that we have PD in the background. So by the cone lemma, any projective set of reals closed under Turing equivalence either contains or is disjoint from a Turing cone. And then in ZFC alone, the intersection of countably many Turing cones contains a Turing cone. So what we can do here is we're going to intersect these things together, and we're going to get a particular model such that that model with all its definable classes has the OIMH. So what we need to do first is for each sentence phi with parameter alpha, you're going to let x phi be the set of reals such that alpha is countable in mx and mx satisfies phi. Okay, just a basic fact about Turing equivalence, the x phi are closed under Turing equivalence, such if x0 and x1 are Turing equivalent, then these models are going to be equal just by unfolding the relevant computations. And moreover, these x phi up here are all delta 1, 2. Okay. So now we're going to pick a Turing cone inside either x phi or x naught phi, right? So we have the x phi here, and we have the x naught phi here, and we're going to pick a cone inside each, right? And we're going to let y be in the intersection of these cones according to whether or not we've picked x phi or x naught phi, depending on which one is empty. Good. So alpha is countable in my, as only one of these Turing cones has reals with alpha countable. And furthermore, if y is recursive in Z, it follows that my and mz have the same theory with parameter alpha. Okay. So F is able to pick an R alpha for each particular countable ordinal alpha. So this F we had earlier is well defined. Okay. Now we can use this to find our model of the OMH. This should be minus ref here. Okay, so we just take large enough h theta with theta regular, and we ensure that F lives in there. And then you just let this model N be N star intersected with H omega 1. So you can think of this thing as the transitive collapse of our initial countable elementary submodel. Okay. This N is going to help us find OIMH ref, or our model of OIMH ref. So we're going to let beta denote the ordinal height of this particular N. And now we do kind of reshaping stuff as we did before and almost disjoint forcing. So we add a real so that NY is equal to L beta Y and is the least model of ZFC minus, this should be a ref here, containing Y. So NY is MY in this context. And in this context, MY with its definable classes satisfies the OIMH ref, and indeed NBG minus ref. Okay, how are we going to do this? So suppose that phi with parameter alpha, for alpha less than beta, is satisfied in a model of an outer model of this particular MY. Okay, we're going to find a particular definable in a model of my satisfying phi. Okay. And again, we use these particular, sorry, I just noticed something came up in the chat. Is the proof of alpha being countable in MR alpha constructive? That's a good question. I doubt it is in polynomial time for sure, because we're just using the relevant model to unfold the relevant computation. It's a good question, though. I will ask Sai about that. I think I just don't know off the top of my head. Thanks for the question, though. Okay, so we're going to find a particular inner model of my satisfying phi. So we're going to do the same kind of work again, where we use this forcing to enlarge and reshape, and then get this model of the form mz, in which m is a particular definable inner model. So since m0 is definable in m, and m is definable in mz, we know that m0 is definable also in mz. And now you can choose an n such that m0 is sigma n definable within mz. And you let psi be the sentence, there is a sigma n definable in a model satisfying phi. Okay, now I should note that here I'm being a bit cheeky. This is actually in the NBG version of the proof, but you can schematize it away if you want to make it all ZFC minus ref and pull back the relevant formulas. So there's no issue there. Okay, so we have this phi with parameter alpha true in mz, and now you pick a particular point that's truing above both z and this fa. You could just let this be the join if you wanted to be in the structure of sharing degrees. Okay, and now you know that z star belongs to mz by assumption, and z is in mz star, since z is in fact chosen to be Turing below this z star. And then you know they're the same model just by unfolding the relevant computation. Okay, good. So now, if you recall the definition of FA, we know that FA was chosen specifically so that for any particular x, MFA and MX have the same theory with parameter alpha, sorry, MF alpha, right? Because we in particular have that x is Turing above FA, okay? Okay, now we know that psi holds in M of FA, and we know that FA belongs to MY since FA was chosen to belong to N. And so we can choose a real Y in MY that's Turing above both Y and FA. Okay. Now we're pretty close. We do kind of similar stuff. So you look at, you know that these two models are equal, since in particular Y is in MY and Y star is in MY and Y is in MY star. Okay, but now since this is Turing above our FA, MY star has the same theory with parameter alpha as MFA. And so psi holds in MY star equals MY. Right? But remember what psi said, that exactly says that there is a sigma n definable in a model of a particular kind. And so we have this in a model of MY as desired. Okay.
Quick question.
Yeah, go ahead.
Is the cone theorem the only place, the only way you're using projective determinacy?
Yes, I'm pretty sure you're just using this to check that this particular f is behaving nicely and is well defined.
Wow.
I'm pretty sure, right? I'm just wondering if I failed to mention it in anything to do with the Turing degrees. I mean, it pops up. It pops up. Yeah, right. It's popping up here as well when we pick the X and X phi. This is part of what's so the cone lemma is kind of in the background all the way down here. We need that any projective set of reals. Yeah, so this is the cone lemma here. We need it to be either contains or be disjoint from a Turing cone. We're not guaranteed that without PD.
Mm-hmm. Thank you.
Okay, good. So we have that the OIMHRF is probably consistent. That's nice. But does it have any, well, assuming that PD is in fact consistent, then it's consistent. But does it have any large cardinal strength? Well, the answer is yes, we get 0 sharp out of it. How much of this am I going to go through? Because this is quite an involved proof, as you can probably see here. Let me just give a sort of sketch of this, because this will take quite some time, and I don't want to. I'd like to talk. People asked earlier about the sense in which things were interpreted, and so I think it would be interesting to talk about that a little bit. So, I mean, the point of this is what you're going to do is you're going to get clubs that are containing kind of restricted indiscernibles in outer models. So this is what this lemma 24 is partly preparing us for. So we get that if you've got any particular parameter-free formula, then you have a delta 1 definable club such that either phi alpha holds for all alpha in that club, or it fails. And then what we're going to do is once we have that, we define the notion of a sigma n indiscernible. So this is just for sigma m formulas. These are the number of free variables you have. And again, you use this kind of reshaping type arguments to end up with clubs in outer models that either satisfy or fail the relevant statements on a club. You reshape them into a real, and then you pull that real back into V using the OIMH. And what happens in the end here is that you get, you're going to get a bunch of sigma 1 indiscernibles in 1 free variable, sigma 1 indiscernibles in 2 free variables, sigma 1 indiscernibles in 3 free variables, and so on. You have all these clubs of these particular kind of restricted indiscernibles in your original model with the OIMH. And then you intersect them all together because you have a countable, definable family of clubs, omega many clubs. Intersect them all together. You have full sigma 1 indiscernibles. And from that, you get 0 sharp. So that's the shape of this particular proof. And I'm not going to go through it because it will take a long time. But that's roughly what we're doing here. And we end up with 0 sharp in Lx, which is what we have here. Okay, good. So sorry for having to skip that, but it was a long proof, and I was suspicious that that was going to have to be the case. I'm happy to talk about it more in questions if people would like. So we're now in a position where we have the consistency of this theory relative to ZFC plus PD, and we can get 0 sharp out of it. So this is nice. We have ZFC with many large cardinals holding in L in a particular theory that implies that every set is countable. And it's motivated on the idea that, you know, anything you can dream up, as long as it only has ordinal parameters, can hold in an inner model. Okay, good. So how does this relate to the things we talked about earlier? So what's going on? Both the countabilist and the uncountabilist look at each other and think the other misses out sets. So the uncountabilist looks at the countabilist and says, hey, you just live in a countable transitive model or H omega 1 at the very best. The countabilist, on the other hand, looks at the uncountabilist and says, hey, you're missing all sorts of collapses by assuming that the power set axiom holds. Okay, so we get quite a different picture of what a foundation looks like on this perspective. So one thing that was asked very, very early on was, okay, what does the generous arena look like? So natural numbers are no problem. Yeah, natural numbers go through fine. But the reals are now a proper class. So maybe you want to use one of these NBG minus based theories. Now, there are some kind of tricks you can use to talk about the reals on this perspective. So one point is that the algebraic reals are elementary in is an elementary submodel of the reals, and there are only countably many of these, right? So we could just talk about the algebraic reals as a kind of ersatz structure for understanding what's going on in the reals.
Neil, is this a good time to interrupt, or should I let you go?
Yeah, you can interrupt for sure. Yeah.
But when we do stuff with the reals, we want stuff beyond just their structure as a field. So we want like the exponential function, trigonometric functions, etc. Mm-hmm. And the algebraic reals aren't getting us that. Mm-hmm. So are you saying we really want to look at not just like the algebraic reals, but like some richer structure with more things added on that's still countable?
Yeah, so in particular, once you start looking at the functions on the reals, right, and you start looking at the properties of the function space, you're gonna, for instance, want to do things like, well, yeah, let me. This will come up on the next.
Okay,
next
then I apologize for like preempting you.
No stress at all. No, it's good to identify. But I mean, this is just one way you could get at some of the structure on the reals. I guess I don't want to say we should just look at the algebraic reals, right?
Sorry, Neil, can I just like kind of along that point? Sure. Maybe you'd have just like the algebraic reals. If you're a countablist, like maybe you'd have the algebraic reals, but you'd throw in like pi and e or something, like throw in a couple.
Yeah, so I guess you can. I should go back to model theory class. So you can, if you extend the algebraic reals with just some additional constants, right, and things like that. This should still be. This will still be countable, right? Yeah, right.
But how would you know that there is like a countable number of pi's and e's, like transcendentals? I mean, we wouldn't know how many additions we would need to do on the algebraic. Do we know that this would be countable?
That doesn't seem that doesn't seem clear to me. In any case, I'm kind of happy with using NBG minus. I don't want to get, let me just press on because I don't want to get,
I mean, if I may just say, Elliot just made a good point. I mean, right, what you're proposing is just a way to deal with this in certain situations. And, usually, or in many situations, you're maybe only interested in something that has a certain complexity. So you could look at all the reals that are definable by something in that complexity, and you would still only have a countable number of them, depending on what the application is, if it's somehow, approachable like that. I mean, I guess if you look at it as an ordered structure and you want completeness and so on, it will be different. But
right.
Yeah.
Right. So there's a big question of what exactly we that's really helpful, Gunter. And I think there's a big question of what exactly you want out of the reals in any particular context here. Let me just press on, and then we'll we can come back to this, because I think this is a really important point, and it's helpful to get your guys' feedback on this. Okay, so you know, in this case, I don't want to dwell on this too much, but you can think about this as analogously, the ZFC-ist can use a countable transitive model in order to study V. So this is a very familiar move. I talk about various strategies here in this this paper of mine that you can read if you like. Okay, so what about bigger objects? So third order, objects of third order arithmetic and higher. So here we do have a difference. So some third order objects can be coded by second order ones. So the continuous functions from R to R, for instance, we get all there's only countably many of those. But other third order and higher, sorry, there's only real, it's only continuum many of those, my apologies. So other third order and higher order objects can be thought of as only living in impoverished ZFC models. So there's this kind of trick we might play is we say, look, we do have lots of ZFC models, right? And so we can just interpret these higher order objects there. They're just not, they're not about the reals. And perhaps if you want to, you want to talk about what you can prove about the reals. So we have R, this is this big proper class here. And I'm looking at some inner model, right? And it's got its conception. This is a ZFC inner model, right? It's got its conception of what the reals are, right, in there, but this is a set in that context. And maybe we want to assert like bridging principles that the R down here, for instance, in certain models is elementarily equivalent, for instance, to the R there. And then, you can use all your higher order resources in your ZFC model to reason about this small model and then export it up to the proper class size thing. So there are kind of moves you can make here. It's, not dissimilar from if I have some small countable transitive V that's elementarily equivalent to V, I can study all the forcing extensions, even perhaps using things like non-definable class forcings over this little model. And then I can export the results back up to V as long as I have elementary equivalence. Okay, so the picture is very, very different, but at least insofar as you want to talk about the reals, the continuous functions on the reals, and just models of ZFC, you can still interpret mathematics or at least the usual things we talk about in mathematics in these contexts. It just looks very different. So this is then going to link in with this idea of a shared standard. So we have a shared standard for interpreting proofs. It's just that the role of ZFC-based proofs is somewhat different. It's about the structure of inner models rather than the structure of the universe. And metamathematical corral is also unaffected. So we can study models of set theory, including the ZFC models, exactly as before, either in the wider world or within some other ambient model we have of ZFC. Now, personally, where I think things get a little more complicated is in risk assessment. So we've answered the motivational challenge via the idea of the universe being saturated under possible sets. But what we don't have is like this clear intuitive description of the universe like we have with ZFC-based set theories. And I think that the kind of intuitive conception behind ZFC-based theories is partly, along with the fact that we've never found a contradiction, what convinces many people that ZFC and its extensions is consistent. Okay, so there's a few points to note here. The first is that if your focus is only risk assessment, or maybe you want to say the iterative conception convinces me that ZFC is consistent and this is validated on the picture that we've presented. I mean, this is somewhat unsatisfying for me. I think it would be really nice if we could actually get some kind of iterative picture out of the Counterbliss perspective. Two possible responses are we come up with some kind of underlying conception in a non-iterative way, but I like the idea of maybe trying to come up with some idea of iterativity. And what one can do here is just say, look, when I iterate stages, really what I'm doing is I'm not getting all sets, I'm getting all possible sets. And for a set to be possible at an additional stage, we might want to have a particular restricted conception of this. So let me just go through this. So one thing you could do is, as long as you have a well order with which well orders the universe in order type, in the same order type as the ordinals, you can develop a hierarchy, right? You just have to feed in the sets slowly. A problem here is that this well order is actually going to be equivalent to the continuum hypothesis in this concept, right? You're saying that every class either has size continuum or is set sized, i.e. countable. And so one thing you could do instead is iteratively add in collapses. So the problem here is you want to find the right collapse, but if you want to think of a Boolean universe being slowly built up, you could basically think, and this is kind of implicit in something that Gunther said earlier, you just say that V looks like col omega less than odd extension. So you feed in the relevant collapses from your Boolean universe at each stage, building over some model of ZFC. So I think this idea of an underlying conception, it's at least open to come up with some idea, but for the moment, I think ZFC is in a better position regarding the background conception. Okay, let me wrap up because I've sort of talked for too long already. So I'll just identify a few open questions we might consider. So first, can you come up with some non-iterative underlying conception for the Counterbliss? Second, what are the available options for stratifying the hereditarily countable sets in order to give an iterative idea? And third, is it possible to find some kind of extensions of the principles that we've considered here that jack up the strength? So give us things beyond zero sharp, or indeed a slightly weaker and give us a more kind of fine-grained analysis of the principles leading up to zero sharp. At the moment, it's a very kind of stark contrast. We have either you're consistent relative to ZFC minus, or you're inconsistent, or you give us zero sharp. It'll be nice to have a bit, a bit more fine-grained like we get with the standard large cardinals picture. And I guess this is a question that's popped up repeatedly. There's a very general question here. So what do you really want set theory for? I mean, is it merely a tool designed to fill certain foundational goals? And if that's the question, I mean, you get a very different picture out, but I'm not sure it's any kind of mathematically worse than the ZFC picture. But if you do think it's part and parcel of our conception of set that it gives you these many uncountable infinite cardinals, then I think there is a problem for the Counterbliss. So really, it's putting pressure on the idea that you can get ZFC set theory just out of these kind of very minimal foundational goals. It seems like there's Counterbliss pictures that do pretty well on that in that regard. Okay, thanks very much for listening. I apologize I had to miss a couple of proofs. For this paper, we've received a huge amount of help from a lot of people. So I just want to extend my thanks to everybody who's contributed to this paper along the way. Thanks.
Thank you. And it wasn't your fault that you had to skip some proofs. So there were lots of questions during the talk, which is usually a good sign, I think.
Oh, I think even if everyone had been quiet as mice, I'd have still had to skip that talk, that proof. It was just a case of wanting to fit too much in. But yeah, thanks for everyone's patience. Yeah, it's helpful.
Okay, so are there any further questions still?
Yeah, I have I guess a comment and a question. So on this matter of the countabilist and the uncountablist accusing each other of missing, there's a theorem that I don't really know very much about. It's quoted in Adrian Mathias's famous paper, Happy Families. He attributes it to Jensen. And what it says is that if you take sort of the one extreme, namely start with the ZFC universe and then do class forcing to collapse all the cardinals. So you've essentially forced everything.
Yeah.
You get a model, a countabilist model.
Yeah.
And at the other extreme, start with your ZFC model and just cut it off at H omega 1, hereditarily countable sets. The question is, are those two elementarily equivalent? And Jensen's theorem says that that statement, that they're elementarily equivalent, is equiconsistent with the Malo schema that says that every closed unbounded class of ordinals has a regular element.
Right, sure.
So the two people arguing past each other could in fact agree, sort of, if we would provide them with a Malo universe, a Malo kernel where they can cut off their universes. The question I'd like to ask, though, is a somewhat more technical issue. NBG doesn't have comprehension axioms for formulas involved quantifying over proper classes.
Right.
And now you're going to have the reals are going to be proper classes and continuous functions will be coded as proper classes and so on. So you won't be able to quantify over them in comprehension schema, and in particular, you won't be able to do proofs. Even ordinary natural number induction won't be available for proving statements that quantify over those complicated things. And I guess my question really is, does the presence of all sets are countable and maybe the presence of the reflection schema compensate for that? Or if not, what do you do about it?
Well, I mean, I know what I would do, which is just move to MK minus. I don't.
That will certainly take care of it, unless it messes up some other things.
Yeah, right. But then the question is that? I mean, but then our consistency proof doesn't clearly work. So that would have.
Right. You may need PD and inaccessible after all those wooden cardinals or something.
Right, and it could be. I mean, it could even be that if you add in. I mean, I don't know how it would go, but if you add in MK, if you consider the theory MK minus plus OIMH ref, that might be inconsistent, for instance. I just don't know. Certainly in the context of the kind of vanilla inner model hypothesis, the NBG version plus the IMH is fine, but MK will conflict with the IMH, and you need to do some kind of relaxing of the or I should say restricting of the outer models allowed in order to get that be consistent with MK. So I mean, my choice would be to look. I'm happy with I'm happy with class theory. I like I like proper classes, unlike a lot of people. So
working with psi, you have to like hyperclasses and a lot of other things.
Yeah, right. You have to go full to full infinitary orders. But I mean, look, that's not necessarily going to be everybody's cup of tea. So it's a really good question if the reflection helps compensate for that. I mean, there's definitely a move in which you say, look, I'm just happy with only induction on the restricted things, but that seems very unsatisfying to me.
It would be nice.
Yeah, I don't know is the answer, I think, whether it compensates. It's a great question. Yeah.
Okay, thank you.
Thanks.
Yeah. A question. Going back, way back, Poincaré famously thought the only infinities were countable infinities. And to what extent does this counterbliss view, would this counterbliss view make Poincaré happy?
Yeah, so I think definitely not. And it is almost somewhat cheeky calling it countabilism, right? Because we still want to talk about the reals as like a definable, uncountable class. And indeed, we want to allow that Cantor's theorem is telling us that there are proper classes. There are uncountable things. It just turns out that every uncountable thing is a proper class. So to the extent that you might want to give an interpretation of class, we get into very kind of thorny philosophical issues about the interpretation of classes here. Maybe you want to give some kind of nominalist interpretation of classes, just in terms of definable formulas, or indeed you could give kind of pluralogic interpretations of classes that are still nominalist. I guess for Poincaré, the crucial thing would be, are you kind of allowing impredicative comprehension over these things? Because that's really meaningless. Mm-hmm. Perhaps he would allow kind of predicative talk about uncountable objects and just give it some kind of nominalist style interpretation. I'm not sure, but look, it's I still want to talk about the reals from a personal perspective. I like the reals, and those are a proper class, so probably I make Poincaré unhappy.
Thank you.
There, Paul Levi has raised his hands.
Hi. Yeah. So the theory ZFC minus ref plus count, is that, and maybe it's a question, maybe Vika also might know the answer to this, is that bi-interpretable with second order arithmetic with dependent choice scheme?
Yes. So this is in, if you want to look up the proof, it's in regular, this is folklore, but Regular Crap has a very nice presentation of it in her dissertation.
Actually, I'd be interested if you give me a reference, that'd be good. But so does that have implications for the stuff that you're doing? Could you transport things you do from the world of ZFC minus ref plus count to the world of second order arithmetic plus dependent choice? Would it be illuminating or helpful? Or
yeah, so it's a good question, exactly like how the different perspective provided by second order arithmetic might influence what's going on here. I come primarily from philosophy and set theory. So, the ZFC, when I hear second order arithmetic, my mind immediately just thinks, ZFC minus plus every set is countable as my preferred theory for working in that context. But maybe, these are, whilst they're in some sense the same, there's also a different perspective provided by working in second order arithmetic. So it's a really good question whether you get a kind of different perspective by working in that context. And I don't know if different principles are suggested, for instance. The determinacy axioms, for instance, are like, very much like principles of second order arithmetic, right? It just turns out that they interact very nicely with set theory.
Okay, right, thanks. I have one other question. You mentioned that you said at one point MK plus bounding. I know what MK is. What's bounding?
Oh, yeah. So it's a kind of choice principle for classes. You can think of it.
Is it plain choice or odd dependent choice?
It is. Vika, help me out. It's for any parameterized theory, any parameterized collection of class. There is a function picking an element out of each.
So it's the weaker version, the non-dependent version.
Yes, bounding is what psi equals the choice.
Okay.
Yeah.
Okay. Then I know what it is. Okay. Thanks.
Yeah. Apologies for my brain not working on that one.
Okay, guys, if you have questions, just fire away.
Okay, so I know Homkins has, I'm not sure if he's really advanced this per se, but at least brought up the possibility of even more radical potentialism, in which there isn't even a true omega, but rather that there are models of arithmetic, and that the power set operator is just so powerful that for any model of arithmetic you find, you can always find a non-standard cut.
Right.
So is that plausible under the same motivations you're discussing here? And is there any research into a parallel program into set theories where we have a weakened, so ZF minus plus a weakened with infinity replaced with a weaker version involved models of arithmetic?
So certainly, I mean, for instance, Cam has done a bunch of work on like the kind of potentialisms you well indeed Vika. I'm probably missing people out in this in this audience, but plenty of people have done stuff on this kind of potentialism. Exactly how it might figure into this context is a really interesting question, because I suppose one wants to take the more kind of arithmetic perspective in that context. I mean, the thing that we like in some sense about these forcing type constructions is that they, even if you have an absolute notion of like transitivity, right? You can think of, I mean, that's part of what kind of motivates that Cohen-Scott paradox I talked about earlier. It's the idea that, look, these collapses you add in, they're not sort of strange in any sense. So they look like they can live in transitive models. So why aren't they there? But yeah, it's a good question if there's a kind of the issue I guess you have is that you don't get this kind of just unioning together models once you have non-standard omega in the picture, right? You can't just bundle two models together and have something that looks nice. So how the and everything is so like radically non-absolute once you give up. Satisfaction is not absolute. How one would get a kind of absoluteness principle in this context where not even delta naught stuff is absolute is really unclear to me. But it's a really good question. So did you mean, I think maybe I'm kind of talking past you a bit, did you mean the kind of absoluteness principles like the OIMH, or did you just mean like more generally richness kind of principles that might be formulated in this context?
Yeah, specifically the richness principles. Like I obviously expect a lot of absoluteness problems once we give up the standard omega, but just the incredibly rich power set operator you could imagine in this context.
Yeah, it's a great question. I don't know. I just don't know how one would like. Do you have a suggestion of how one might formalize that?
Yeah, like I said, you can replace. So first off, you have to get rid of choice because you wouldn't want well ordering, but also change infinity from the existence of omega to there is at least one model of P on arithmetic, and all of them are non-standard.
Yeah, it's a great question. I just don't know what would happen there. Yeah, good question, man. Don't know what to say. I'll have a think about it. I like this idea though. I mean, it'd be nice if one could get something out in this context, because this will give you a kind of a really like radical perspective on maximality. I mean, now that I think of it, I know that Oystein Linnerbo and Joel have a paper on these potentialist maximality principles that are formulated modally, but I can't remember if they look at it in a kind of radical potentialist context where you have non-standardness like that.
Okay, Miha, your hand is still up. Do you still want to ask a question? It's too bad that we're not able to just go to the ginger man now. It feels like this would be exactly the kind of conversation one would have there. But anyway, we are here. So
we lost so much. I think I have a more technical question, but I'm not sure. So you showed us that the version of the inner model hypothesis where you allow any kind of parameter is inconsistent. And so I'm looking at your handout. And so the parameter that, okay, roughly speaking, you go to this outer model that's like an L alpha of a real, and then you pull that statement back. You haven't really used any parameters yet. But then you do it again with this failure of collection function, and here you use a real parameter. And okay, it might be this L alpha of R parameter that you've pulled back, or it might be the function itself. I'm not really sure. But so my question is, so these reals that you build, these are all added by this coding forcing, or what, this almost disjoint coding and this reshape forcing. And so can you remind me, these are all very benign? I mean, almost disjoint, well, I don't know. I mean,
so it's the
countable. I'm used to saying if it's CCC, then it's benign, but now everything is countable. So I'm not
Yeah, so these I actually got the paper up so I can point to it, because it is a little bit fiddly. So this is Carolyn and Sai's paper, and we want theorem 3.8 and 4.1, I think. Should have prepared this before.
Well, I mean, it's not. The reason why I'm asking is, I'm thinking about one of the questions you had at the end, where you would want to modify the space between all parameters and ordinal parameters somehow.
Right.
If the bad parameter here was added by this very benign forcing, right, then I'm completely at a loss what you could possibly do. I was thinking, maybe instead of all parameters, you say, well, maybe I'll allow reals that appear in a nice forcing extension. But if a bad real appeared in this almost disjoint coding and reshaping extension, then
I think once you have class forcing in the picture, that these are pretty benign. They are, I think, this is all distributive, if I remember correctly. So this was originally done in this kind of set MK context. This is essentially a ZF, kind of like a ZFC minus context, but it goes down to the case of where you've got count in the picture. So yeah, you have this particular family, and then I'm sure it was distributive.
Yeah, I think it's right. It's countably distributive. Reshaping forcing.
Yeah, there you go. P is definably distributive in this particular context. Yeah. So they're pretty innocent, right? in terms of forcing constructions. So yeah, I don't think that you do need real parameters though, and this is why I'm sort of at a loss as to what any sort of modification might be beyond ordinal parameters, right? I mean, it just seems like you even have quite innocent, real parameters. I mean, I suppose one thing you might do is look to restrict the forcings, but then, these are not particularly crazy class forcings in the class forcing world. So yeah, this is kind of one of the tricky things. There's like formulating something that doesn't go too far is tricky in this context.
All right, thank you.
Okay, guys, I don't know about you, but it's 10 minutes to 4 now. I think it would be maybe a good time to call it a day, unless there's a really pressing question still. Okay. I think, okay, great. Thanks again for this really inspiring talk. Very interesting stuff.
I have to thank you folks. This is some really interesting questions. So I'm looking forward to thinking about them. And I'll just put my email in the chat if anybody wants to fire an email and talk about this more. That would be great.
Thank you.
All right.
Great.
Thank you for the great talk.
Cool. Thanks very much.
Okay.
Bye. And I have an announcement. So Adrian is speaking for the next 2 weeks, and his abstract is going to go up on Monday. He's a bit late with it.
Okay. Looking forward to it.
Yeah, check back during the week.
All righty. Okay. Until next Friday. Bye-bye.
Ciao.